So as you see from the title, I'm still going to discuss some non-equilibrium properties of long-range interacting systems, but I would like to provide you a different point of view, which is the one of non-equilibrium stationary states. So this is a typical approach in non-equilibrium statistical mechanics. Basically, we still can consider a class of simplified models in low dimension, let's say a chain, and you can attach this system to external reservoir and impose some gradient, let's say a temperature gradient. And one typical question is, so to understand the relation between the macroscopic dynamical details and, let's say, hydrodynamics, so macroscopic behavior. For instance, you can find on the macroscopic scale a Fourier law in this form for heat conduction, or in some cases you can also find some breakdown of the Fourier law where you find a heat conductivity that is not constant but it diverges. So overall, in the framework of a short-range interacting system, this scenario is more or less clear, I would say. On the other hand, if you consider long-range system, the situation is much less clear. So we decided a bit to explore this part. So here, as you see, I'm considering this class of model in one dimension. So they are Hamiltonian model where you have a two-body long-range interaction. Here, look at this denominator. You have again this dependence, this power law dependence on the distance between sides. Alpha is again this long-range exponent and goes from 0 to infinity. Infinity means that you have nearest neighbor interactions. And again, you have this factor N0, which is the Katz prescription that allows us to have extensive energy, even in the long-range case and in the thermodynamic limit. Okay, so here are some peculiarities that you find when studying stationary states. So they are not independent, but so in this sense they are interdependent. Again, we have a non-additivity for alpha less than D. So this, of course, affects already equilibrium thermodynamics of long-range systems, but also non-equilibrium one, as we said before, you have non-negligible boundary effects in some sense. The second point is about the linear spectrum. Of course, in these systems, you can compute normal modes in the same way. And in this case, you can find some strange situation where the group velocity of your modes can diverge. So what is the meaning of an infinite velocity? Basically, this is telling you that you don't have proper phonemons in your system. Indeed, if you perturb locally your chain, your system, you will find you don't find the typical light cone propagation with a constant velocity. On the other hand, as it was found in this paper, you find a much faster propagation, which is exponentially fast, and it is ruled by the maximal Lyapunov exponent. So you have this peculiarity. The last point is concerns the system bath coupling. So usually this parameter is in the case of a short-range system is not so relevant. I mean, if you want to perform some simulation, you have to fix it to some value. But the relevant scalings that you obtain, for example, about currents and so on, it does not depend on the choice of this parameter. In the case of long-range interacting system, the situation changes. And if you overlook this point, you may extract wrong information. Let me go a bit into detail. So here is our chain. Here you want to attach it to external reservoirs. And here I'm showing some results about the rotor chain where you have this interaction potential. But bear in mind that this behavior is general, so it does not depend on the choice of the potential. So let us introduce this L, which is the number of thermalized sites. So in this picture, basically you have 3 thermalized sites on the left at TA and 2 at TB. Okay. So okay, you can set up simulations and extract the stationary fluxes, and you study their behavior as a function of the system size. And you see here I'm showing you 2 different situations. The upper panel is refers to the case where you where you thermalize a finite a finite fraction of the overall sites, which is extensive, and the lower panel you just thermalize a finite number, let's say 1. You just thermalize the first oscillator and the last one. What is evident here is that as soon as you enter the strong long-range regime, alpha less than 1, you have different behavior. And where in the case of extensive coupling, you have a constant scaling of fluxes as a function of the system size. Moreover, if you look at temperature profiles, you find this strange situation where, again, once you enter the strong long-range regime, you have basically flat profiles, despite you are imposing temperature gradients. So in order to understand what's going on here, it's useful to give a closer look to stationary currents. Here I'm showing the matrix of stationary currents, J, from site I to site J, okay? So this matrix is antisymmetric, and I'm showing you some decreasing value for decreasing values of alpha. So in the limit alpha equal infinity, you have basically that your matrix is as entries, non-zero entries in the upper diagonal and the lower diagonal, okay? Because of nearest neighbor interaction. And you see that if you take alpha equal 2, basically you have more or less the same behavior, a little bit smeared. But as soon as you decrease alpha and you enter the strong long-range regime, you see that the structure of this matrix completely changes. By the way, here we are working with periodic boundary conditions. So we have a heat bath at the beginning of the chain and the second bath in the middle. So basically, if we analyze alpha equals 0, we understand that in this case, basically each side of the chain is in contact both with the hotter reservoir and with the colder reservoir, so that you have basically a condition where you have a collection of short circuits between your reservoirs with no proper conduction. So these actually can explain the scaling that I was showing before. Interesting, okay, you can say, okay, a posteriori this situation is a bit trivial, but what is not trivial is that if you take an intermediate value, alpha equal 1, let's say, you have this intermediate condition where you have both this configuration, and indeed you can decompose your flux in 2 components: a proper conduction component where you have a heat transfer, and this short circuit way of transferring. Okay, so this is a part of the story. Of course, you can imagine to study also the so-called weak long-range regime, alpha larger than 1. And here I'm showing you some results we obtained with the long-range phi to the 4 chain. So the model is this one. As you see, there is a local pinning potential, which is quartic, plus a long-range quadratic interaction. Okay, this model is not integrable. Interestingly, in the case of the double well case, has the same universality class of the long ranges in model. And indeed, in the case of ferromagnetic interaction, it displays the same phase transition that we saw in the previous talk. So in this case, we did some equilibrium simulation to investigate the hydrodynamical behavior. So basically, the idea here is to observe the correlations of fluctuation of energy density field. This is the local energy on site I, and to compute correlation. So equivalently, you can compute Fourier transform of this quantity and extract the so-called structure factors. Or you can compute the so-called excess energy correlations. So you partition your chain in a certain number NB of boxes, and you compute in time the behavior of fluctuations of this field with respect to the average value. So here are some results for the single well potential where there is no transition, so the simplest case. And you see that there is a rather clear scaling relation for what concerns the structure factor that is amounts to these results. Basically, for you see there is this dynamical exponent ZH. Z is equal to 2 for alpha larger than 2, and basically this accounts for standard diffusion. Whereas if you are in between 1 and 2 in alpha, you have a super diffusive propagation of fluctuations that as Z is equal to alpha. These results actually is confirmed from the excess energy correlation. Basically here are the rescaled curves. You can compute in time the spreading of this distribution and the decrease of its height, and again you find the same exponent. So this is the result for the double well potential. Actually, I don't need to show you again these plots on structure factors, because actually nothing changes. So what we found is that despite the presence, for instance, of the phase transition, the result is always this one. So diffusion for alpha larger than 2 and super diffusion, which is quite unexpected, because one could have thought that the presence of a phase transition, at least something could have changed. At this point, we asked, so is it possible to derive some simplified model that accounts for these two different regimes? The simplest model that you can define is a level flight process for energies. So suppose you are considering your configuration of energy, you can introduce this master equation, linear, where the transition rate are, again, scaled as a power law with an exponent nu. Given the linearity of this model, you can find the asymptotic solution, starting from a localized initial condition, and you find these two different regimes. So basically, you have the first regime is a Gaussian spreading for nu larger than 3, and then you have a sort of anomalous scaling where you have this relation between this beta exponent and nu for nu between 1 and 3. So actually, you understand this different regime because actually this function f has a diverging variance in this case. So nicely, we found a complete correspondence between this simplified model and our results. If we put nu equal alpha plus 1, yes, unfortunately, so we weren't able to find a simple physical interpretation of this correspondence, but it works. And in this model, in this simplified model, you can compute out of equilibrium states, and consistently you find the diffusion. So the typical scaling of flux is 1 over n, which is related to diffusion and super diffusion. If we go back, so you now ask, so is it possible to observe this super diffusive regime in the original model, the deterministic model, yes, actually, so this is a very, so it's not so easy to perform a simulation in this case, because when you deal, as you may imagine, when you deal with long-range interaction, finite size effects are really, really important. So if you want to see this super diffusive scaling in fluxes, you need to consider very, very large sizes, very, very long times, so it's not so straightforward. In this case, where you have super diffusion, moreover, we find this the temperature profiles accumulate to a strange limit profile, which displays a sort of divergence in the origin. So, by the way, this V shape of the profile is because we are dealing with periodic boundary conditions for technical reasons. Okay. And let me conclude with open problems, because for what I've told you, you may imagine, okay, more or less the situation about long-range interacting systems and conduction is more or less understood. Actually, it's not, because if you consider different models, here is the case of the long-range Fermi-Pasta-Ulam model, so where you consider basically a long-range potential which is quartic, you don't find any agreement. Here I report the Levy flight prediction of the stochastic model, which is very far from the observed data. This model is moreover displays also in the short-range case an anomalous scalis, which is given by the Carter-Parisi-Zhang exponent. But you see that it displays also a very, very slow convergence to the short-range limit. So this confirms that the Fermi-Pasta-Ulam model, again, is a quite problematic model also in long-range case, but it's not limited to the Fermi-Pasta-Ulam model. You can consider, for instance, as it was done here by Tamaki and Saito, a harmonic long-range potential plus an harmonic pinning and random collision. So the advantage of this model is that it is solvable because you have a linear deterministic part plus stochastic fluctuation. So you can perform some analytical results. And they found a super diffusive transport in a different interval. So in this one. So this tells us that the situation is the overall framework is not clear, and this possibly suggests the existence of different hydrodynamic universality classes. Again, we have to keep on studying this problem. Okay, stop here, and I thank you for your attention.
Thank you, Stefano. Yeah, questions?
Well, I found your talk very interesting, especially the part concerning Levy processes, because I am interested in Levy processes. But I have a question that for something I'm a little bit confused, because what about the Fourier law, right? Because I remember that many years ago I was contacted by somebody claiming that the work done by people from Florence, which is was not correct, and for a paper published on Nature, and so there was a statement that the foundation of the Fourier law, theoretical foundation of Fourier law, was not done correctly by them, and there was a fight. I would like to know what it is, what happens. Can you consider there is the Fourier law is funded, or is still the object of a research? I remember Giulio Casati told me that he was looking for the foundation of
Yeah, I mean,
so can you, do you have any, can you tell me something about that? Because
limiting ourselves in the case of short range systems, I would say that okay, you obtain this Fourier law. You can study some models and which show that the emergence of the Fourier law. There is also a class of models that actually does not produce the Fourier law, so which is related to this anomalous transport phenomenology. And so, but this is again is related to the dynamical properties of your system. So.
But the model is not reproducible. Does it mean that the Fourier law is not yet proved?
I mean, yes. I mean, you cannot. I mean,
the story goes in the following way. I mean, in low-dimensional systems with the momentum conservation and invariant under time translation, Fourier law is not valid. There is anomalous transport, and there are rigorous proofs. The most recent proofs some years ago are given by Herbert Spohn and collaborators. Fourier law in, say, three dimensions, no one is questioning it. The point is when you deal with low-dimensional system, low-dimensional means one dimension, two dimensions. That's hydrodynamics. The usual hydrodynamics doesn't work, and in those cases, you have to expect anomalous behaviors, meaning that the Fourier law is not satisfied. That's the shortest way to summarize it, okay?